This is recording for AQA Further Pure Mathematics, Algebra and Graphs, section 1.3. We're looking at the turning points of graphs. Well, first of all, I'd like you to consider this function, y is equal to 1 over x squared plus x minus 2, which we can factorize the denominator to 1 over x plus 2, x minus 1. So if we were to look at sketching this graph, first of all, we might want to look when x is equal to 0. We can see that y will be equal to negative 1 over 2, so negative a half. In other words, it's going to cross the y-axis at negative 0.5, about here, let's say. And we can see that when x is large, so x approaches plus or minus infinity, then y approaches 1 over x squared. The x term and the minus 2 are going to be negligible compared to x squared. So it's going to look like 1 over x squared for large values. The asymptotes are going to be where the denominator is equal to 0, so there are asymptotes at the values of x equal to negative 2 and x equal to 1. So if we mark those on our graph, there's an asymptote coming down here at negative 2, vertical asymptote. There's one at 1 here. And we know that for large values it looks like 1 over x squared, so it's here positive and positive. And what about between negative 2 and 1? Well, if we consider that, we can see that between negative 2 and 1, x plus 2 is positive. So if I write this down, between negative 2 for x and 1, x plus 2 is greater than 0, but x minus 1 must be less than 0. So there we've got a positive value and a negative value multiplied together. So therefore y must be negative. So for all the time between the two asymptotes, y is negative. So therefore it must come from this position here and finish down here. Now put those together and we'll get a sketch of the graph which looks like this. Now we don't know exactly where the maximum point is after it goes through the negative 0.5 there, but we know that it must be less than 0. So we know there's a maximum point on the graph, and the graph sketch looks something like that. Note that that point at negative 0.5 is not going to be the maximum value. So a rather neater sketch now on my diagram. But the question now is, well, can we find where that stationary point is, where the maximum point is? So what we can do is to consider a straight line y is equal to c. So between those two asymptotes, if we draw in the line y equals c, then you can see that at this point here it crosses the graph into two places. However, if I was to move the line, then it could cross at 2 or even no intersections at all. So if you see the line moving up there, you can see that at the present position it's got no intersections. But there was one particular value where there is just the single intersection point there, and that's at the local maximum. So the local maximum is going to be at the point where the line y equals c has got one solution when we try and solve it with the graph of y equals 1 over x squared plus x minus 2. And that's what we're going to do on the next slide. So if we now call that particular value where there's one solution k, then the solution will be where k is equal to 1 over x squared plus x minus 2. So in other words, we're just equating the y values at that point. try to solve that, we get therefore that k times x squared plus x minus 2 would be equal to 1, or that gives us kx squared plus kx and then minus 2k minus 1 is equal to 0. And this we can solve. It's a quadratic, we can solve, but if we want only one solution, then when we solve it, b squared minus 4ac must be equal to 0 for one solution. And that means that k squared then minus 4 multiplied by k multiplied by negative 2k minus 1 must be equal to 0. So that's our condition for there being one solution. And if you simplify that, we find that 9k squared plus 4k is equal to 0. And so therefore k is equal to 0, or k is equal to negative 4 over 9. But we know that k is less than 0. So k less than 0, that means our value of k is negative 4 over 9. So the y value at the maximum point is negative 4 over 9. We can now substitute that into our initial equation, into this one up here, and therefore we get that negative 4 over 9 multiplied by x squared plus x minus 2 is equal to 1. And if you solve that, you will, by multiplying out, you should be able to get to 4x squared plus 4x plus 1 is equal to 0. That's a perfect square. 2x plus 1 all squared is equal to 0, and therefore x must be equal to negative 1/2. Therefore we found our maximum point at a value of x is equal to negative 1/2 and a value of y equal to negative 4 over 9. So the method there is one where we're not using any calculus. Some of you may have met calculus where we can find maximum points by differentiating, although this is a function that you may not yet be able to differentiate. So this gives us an alternative method where no calculus involved. We're simply using the idea that the solution to the two equations simultaneously has got only one value. The next slide is all written out a little bit more neatly for you. So you can see there that our maximum point, negative 1/2, negative 4 over 9. Well, that is the end of the methods for finding graphs of rational functions. There's one more video, however, section 1.4, where we'll just look at one or two harder examples of sketching graphs.